Hello, welcome back to my two-part talk about the local to global principle for analysis of subgroups. In part one, we talked about undistorted subgroups, which is the special case of analysis of subgroups in negative curvature. And we talked about how representations from diagonal space fit into the picture. We talked about the Morse lemma for quasi-geodesics in hyperbolic space. We talked about how the local to global principle implies stability for undistorted subgroups in that setting. Now in part two of this talk, we will say something about higher rank symmetric spaces, which are generalizations of hyperbolic space. I'll have to define Morse quasi-geodesics, which lets you give a definition of analysis of subgroups that directly generalizes the undistorted condition. That definition and also the local to global principle for Morse quasi-geodesics is due to kappa Vichli T. And after we discuss all that, I'll discuss a quantified explicit version of the local to global principle where you can produce that scale L explicitly. And a couple applications of that. For example, there's an algorithm to check the Anosov condition, and there's also a way to produce explicit perturbation neighborhoods of Anosov representations. Okay, so in this talk, maybe there's two kinds of people, some people who are extremely familiar with symmetric spaces and probably don't even need this slide. And there's maybe other people who are less familiar. So what I've done is I've done a sort of left side where you can just focus on one particular example for the talk, and a right side where I've given the more general definitions. So you might as well say that our group G, it could be any real semi-simple Lie group with finite center. But for the purposes of this talk, it might as well be SL3R. K is a maximal convex subgroup of G. So in this case, that's SO3. There's an associated symmetric space, which is G mod K. In this case, you can think of X as the set of inner products on R3 that all have the same volume. And you can give an explicit model for that symmetric space as the real 3x3 symmetric positive definite matrices with determinant 1. In general, you would be looking at a symmetric space of non-compact type, which is a Riemannian manifold that's not positively curved, and G acts on X by isometries. Another important object that we should pay attention to are the maximal flats in X. In this case, in SL3R mod SO3, a maximal flat F is given by the diagonal matrices whose diagonal entries multiply to 1, and their entries are positive. This is just the diagonal matrices that show up in X. Okay. So to compare the higher rank setting to the hyperbolic space setting, the difficulty arises in the fact that we now have flats, Euclidean spaces of dimension at least 2. That's the completely different situation compared to before. Before we had negative curvature, now we have curvature 0 appearing in some directions. A maximal flat in a symmetric space is a totally geodesic subspace of X, isometric to Euclidean space, and then maximal here means maximal with respect to inclusion of subspaces. The rank of X is the dimension of a maximal flat, and the group G acts transitively on the space of maximal flats or even pointed maximal flats, so the rank is a well-defined notion. And like I said before in the previous slide, this set F is it's a flat. It's a maximal flat because basically because the centralizer of the set of diagonal matrices is really no bigger than the set of diagonal matrices. So if you want to stay in X and also being and also commuting kind of corresponds to curvature in this setting. So this set is two-dimensional and it's maximal, so the rank is 2. And there's a dichotomy here, just to rephrase what I said already, the rank of a symmetric space is 1 if and only if X is negatively curved. In that case, geodesics are maximal flats, so geodesic is always a flat. So for example, HN, when I drew a maximal flat here, just a geodesic. And then the dichotomy has the other side of it, which is that your rank is at least 2 and you can find an isometrically embedded R2 in your X. So that's a total geodesic subspace that's isometric to R2. So for example, the set F is such a thing. It's isometric to R2. What's wrong with R2? So you probably think that R2 is a really nice space that you're very familiar with. But this is where the trouble creeps in to the techniques we were talking about in part one. So first of all, the Morse lemma fails. The Morse lemma said that every quasi-geodesic was within a bounded neighborhood of a geodesic segment. And that fails here. So there's something called a logarithmic spiral. I'll just draw a little picture. And this logarithmic spiral leaves every bounded neighborhood of every line in R2. And that tells you that the Morse lemma fails. I think in polar coordinates this is given by t log t. Also, the local, so we would have used the Morse lemma to prove the local global principle. Now it could happen that you don't need to use the Morse lemma to prove the local global principle. But in R2, the local global principle itself also fails. So what I've drawn here is a rectangle, or you could draw a square. Let's say you draw a square of side length L, and you consider a local quasi-geodesic. So you consider traveling the square, traversing the square over and over. That's a local quasi-geodesic. Basically, the worst thing that happens is you travel a corner where you pick up where you're inefficient by a rate of square root of 2. So this is a square root of 2, comma 0 local quasi-geodesic. But you keep returning to the same point over and over, so it's definitely not a global quasi-geodesic. So the local global principle also fails. And then even going even further, you would have used the local global principle to prove stability, but you can't even hope for stability. That also fails. So undistorted subgroups are not stable in higher rank. This is an example of Yuruki shard. Maybe I won't explain this in full detail, but the point is that you can find a representation of a free group into PSL2R times PSL2R. If you want, you can, with undistorted image. So here you're supposed to think of either a left invariant metric on this Lie group, or think about the action and orbits in the associated symmetric space. In this case, the associated symmetric space is H2 times H2. So this image is undistorted, but you can find representations arbitrarily close that fail to be discrete or fail to have finite kernel. And that's what this picture is supposed to say. So how do you construct this specific representation? So you imagine putting a hyperbolic structure in a pair of pants where two of the cuffs map to loxodromic elements, things conjugate to diagonal matrices with distinct entries, and the other element maps to something parabolic, so something with repeated eigenvalues plus or minus 1. Then you find another representation where you map one of the cuffs still to a loxodromic element, but the one that you map to a parabolic now maps to a loxodromic, and the remaining one now maps to something parabolic. So you can see that this representation is undistorted, and basically the gist of that argument is that every long word spends enough time in either, let's say, this cuff, or either in this cuff or in this cuff, so that in one of these representations, at least you can find in one of these representations, that cuff is getting mapped to a loxodromic, and then in that representation, the distance that you move a base point picks up the length of the word. On the other hand, what you can do is you can deform this representation by finding representations nearby where you replace this parabolic with an elliptic element of, with a sequence of elliptic elements converging to the parabolic element you had. And then you can see that these representations fail to be, each such representation either fails to be discrete or fails to have finite kernel. Okay, so the undistortion condition is not quite the right one if you're still in agreement with my slide from part one, where I talked about what aspects of technical theory do we want to generalize. We want stability. So we need a stronger condition than undistortion. So to phrase and find that condition, we're going to zoom into the structure of symmetric spaces. The condition is going to end up being something equivalent to Nassau representations, But I'm going to just focus entirely on the structure of symmetric spaces and the coarse geometry of these representations and phrase everything in that world. Okay, so the next thing I need to tell you about is Weyl chambers, which is part of the structure of symmetric spaces. So we're zooming into a maximal flat F, such as this one. You consider the restriction of the group G that stabilizes F and stabilizes this point P. So stabilizes this pointed flat. And then you restrict this action to the flat. And what you get is a reflection group called the Weyl group. The Weyl group is generated by these reflections in these walls. These walls are intersections of this flat with other maximal flats. And these walls cut up F into chambers. So one of the chambers is given by V, and it's the set where A1 is at least A2 is at least A3. And the way that the Weyl group acts on this maximal flat is by the permutation group S3, is by permuting the 3 diagonal entries. So any ordering you would think of corresponds to one of the chambers. Okay, great. So we say that the points that do not lie in the walls are regular points. And if you pick two, yeah, let me keep going. Right, so point Q and B is regular if it is in the complement of the walls. And we also actually need to quantify regularity for this whole thing to work. We say that a point Q and V is alpha naught regular if the angle it forms with the wall is at least alpha naught. Okay, so so seeing Q from P, the angles that you form with the walls is at least alpha naught. The same for the other one. The purpose of this definition is that you can imagine sitting at P and drawing a vector out in the direction of V. And if you draw a regular tangent vector, a vector in a regular direction, then any perpendicular plane, so you choose any other tangent vector perpendicular to F, and that 2 plane will always be negatively curved if the tangent vector you choose is regular. As you choose a tangent vector in the walls, if you choose a tangent vector closer and closer to the walls, you can achieve smaller and smaller curvatures, including curvature 0, once you're actually at the wall, right? Walls are intersections with other maximal flats, so there are flat directions perpendicular to the walls. So the alpha naught regularity condition guarantees that the tangent vectors you choose, every perpendicular direction has curvature bounded away from 0 in a uniform way. So that's the crucial concept here. We're achieving a uniform negative curvature behavior by asking for this quantified regularity. Okay, so we're on our way to defining Morse quasi-geodesics. We're going to pay attention to alpha naught regularity. And we're also going to need to replace the concept of a geodesic segment with something a little bit more flexible, with something called diamonds. So if you have a pair of points and this geodesic segment joining them is regular, so it lies in the complement of every wall as seen from P, then there's a unique maximal flat containing P and Q. Q lies in a unique Weyl chamber based at P, same for P as seen from Q. And we define the diamond joining P and Q to be the intersection of those 2 chambers. That's what this picture here is supposed to look like. In this case, the diamonds really do look like diamonds. That's the reason for the name. Now we need to beef this up a little bit and guarantee those uniform negative curvature conditions I mentioned by talking about alpha naught truncated diamonds. So instead of using the whole diamond that you had before, you truncate by throwing away those directions that meet that form an angle less than alpha naught with like base at either P or Q. Okay, so that's what this page talks about. And now I can tell you the definition of Morse quasi-geodesic. I think before I tell you the definition of Morse quasi-geodesic, I'm going to review the Morse lemma. So the Morse lemma said that for every quasi-geodesic, you could find a pair of, and for every subsequence of your quasi-geodesic, you could find a pair of points. So the first point was within D of P, the last point of the subsequence was within D of Q, and every intermediate point was within D of the segment. Let me go back. Now, in the definition of Morse quasi-geodesic, it's actually really similar. We're basically assuming the Morse lemma holds for this quasi-geodesic in a suitably modified sense. So we have a quasi-geodesic xn, and we say that it is alpha naught d Morse if for every subsequence we can find a pair of points p and q, so that the first point xn is within d of p, the last point xn is within d of q, and every intermediate point on the subsequence is within d of this alpha naught truncated diamond. So one way that you can view the Morse lemma in hyperbolic geometry is to say that every quasi-geodesic in Hn is a d-Morse quasi-geodesic. In hyperbolic space, the notion of regularity isn't meaningful because, because maximal flats are already geodesics, so you can't really stay away from walls. It's probably best to think of actually every geodesic as being regular in a hyperbolic space. Maybe that's, anyway, for the purposes of this talk, that's probably the best way to think about it. Okay, now I'm ready to tell you a definition of analysis of representations via Morse quasi-geodesics. I call this a definition slash theorem. The original definition of analysis of representations for fundamental groups of negatively curved manifolds is due to Laborie. And then Guichard and Wienhard generalized this definition for arbitrary word hyperbolic groups gamma and arbitrary reductive the groups G. You might as well might as well assume that G is semi-simple. Kapowicz, Lieb, and Porti proved several other characterizations of the Anosov condition, and this is one of them. So for the purposes of this talk and this work, this is the only definition we need, but it's a theorem that this is equivalent to the other definitions that you might be familiar with or interested in. Okay, so we say that a representation rho from gamma to G is an Anosov if any orbit map gamma to X sends geodesics to alpha naught D Morse C1, C2, C3, C4 quasi-geodesics. Remember that before we said the unassorted condition was equivalent to the orbit map sends geodesics to quasi-geodesics. So we've beefed that up by asking these now to be alpha naught D Morse. Okay. So now there's a basic proposition. Anosov representations are discrete with finite kernel and stable. One way to prove that proposition is to use a local global principle for Morse quasi-geodesics that was also proved by Kapowicz, Lieb, and Porti. It looks a lot like the one from before in hyperbolic geometry. It says that for every alpha naught and new parameter alpha nu, that's less than alpha naught, so it's less strong than alpha naught, as well as parameters D, C1, C2, C3, C4, there exists a scale L, so that every L local alpha naught D Morse C1, C2, C3, C4 quasi-geodesic is an alpha naught prime D prime Morse C1 prime, C2 prime, C3 prime, C4 prime quasi-geodesic. So one way to rephrase this is for every possible quality of local Morse quasi-geodesic, if that quality holds on a large enough scale L, then you actually have a global quasi-geodesic. In fact, even baked into this statement, if you like, you can, alpha naught prime here equals alpha nu. So you can actually guarantee some new quality, some new regularity parameter. It's baked into the statement. There's other things you can control if you want. And I won't go into every step of it again, but this proposition works exactly the same way as the previous proposition about undistorted subgroups. Now that we have a local to global principle, you can simply run through the same machinery and you get that Anosov representations are stable. It was already known that Anosov representations were stable since the work of Laborie, but this theorem gives you another way to prove it. Okay, so something else that I want to tell you about is a sort of reproving of this that I did, where you can find an explicit scale L for this local parameter. So when Kapowicz, Lieb, and Porti proved it, you knew there existed some scale, but it wasn't clear how to actually estimate that thing. So that's what I did. So here's one application. Here's an algorithm to check the Anasov property. It's very similar to the classical algorithm that you could have used for undistorted subgroups. If you have a group gamma that's chromophyperbolic, you choose alpha naught D C1, C2, C3, C4, and you compute the L from the local to global principal. Yeah, and then you enumerate the geodesics of length L, most L in gamma. Then you perform a finite check. You check if, so to enumerate geodesics, you need to use that gamma as chromophyperbolic. So that takes some effort, but you can do it. Then you check if the orbit map sends each of these truncated geodesics to alpha naught D Morse quasi-geodesics. And if so, you've checked that on an L/2 ball at the identity, this local Morse quasi-geodesic condition holds. And since the group action is biasymmetries, you can translate that condition all over the orbit map. And that implies that the orbit map is an L local alpha naught D Morse quasi-geodesic embedding. And if that holds, then you're done. Otherwise, you just relax each of these parameters, and then you continue iterating. So this is an algorithm that you can use to check the Anasov property. Since you can explicitly compute L, you could actually program this. But unfortunately, if you did, it would take a really, really, really long time to run. So sort of like a back of the envelope calculation. I mean, it's hard for even the simplest examples that I come up with that you would be able to run this algorithm. And even the first step, run it on words of length less than like 10,000. So it's that's a drawback for sure. So here's a different application that you can use this explicit local to global principle for. So what I've done is I've given you an explicit representation of the fundamental group of a surface here. This is actually the exact same representation that I had on my second or third slide. I had a representation of the fundamental group of a surface of genus 2 in PSL2R. Then I lifted that to SL2R, and I just put it in a block matrices with the, sort of forgetting the middle. If you just sort of forget the middle row and columns, then it's exactly the representation I wrote before. So these include into SL3R, and they generate a subgroup, and that subgroup is an Anasov subgroup. It sends geodesics to Morse quasi-geodesics because it acts on a copy of the hyperbolic plane and the associated symmetric space, 3x3 symmetric positive definite matrices. And now you can compute the Morse quasi-geodesic parameters for that action. So the alpha naught D, C1, C2, C3, C4, you can compute those. And running through the proof of stability, you can see how far you can perturb a representation so that it still is a sends geodesic to Morse quasi-geodesics. And then you get this theorem. I guess there's one more step. You have to control how the generators affect words of pretty large length. So there's one more step. This theorem says that if rho is any other representation of gamma to SL3R, so that the distance between the generators, so under rho of S and S itself, is at most 10 to the minus 3.7 million for all S in this generating set S, then rho is an Anasov. So here by distance between generators, I mean just use the difference between the matrix entries. So just look at each difference between each matrix entry and make sure each of those entries is less than this number. If that holds, then rho is an Anasov. So this is a really, really tiny number, and it's fair to guess that the actual perturbation neighborhood is much bigger, but there's really not any other general methods for constructing explicit perturbation of Anasov representations. Oh, and since this is a question that I've had before, this calculation that I did is just for this specific group, but the work of Kapovich-Lieben-Barty and also my explicit local to global principle applies to all semi-simple D groups G and all possible symmetric spaces. And on top of that, in this talk, I've only talked about the flavor of Anasov where it's appropriate to consider maximal flats. That corresponds to B Anasov representations, Borel Anasov or minimal parabolics. And actually, this whole story works. So the stuff due to captive sigma T and also myself all works for the general flavor of an L sub where you use other parabolic subgroups. That's a little bit more subtle. You have to think about parallel sets instead of maximal flats. Okay, thank you very much for your attention. Definitely reach out if you have any questions. It'd be my pleasure to answer them or discuss anything you're interested in. Thanks.